So I'm given two matrices, T1 and T2. I'm told one is a reflection and the other one is a rotation. So the first thing I have to do is find a set of fixed points for each transformation. So fixed points, the matrix will when I operate that matrix on a coordinate, the same coordinate will come out. That's how I find what the fixed point is. So for the first matrix then, for T1, I take the matrix 0, 1, 2, 1, 3, 0, 1. I operate that matrix on the coordinate xy. I need to put a 1 there to make it into a, so that I'm able to carry out the multiplication, and that when I operate that matrix on that coordinate, the same coordinate has to come out for a fixed point. So I just use the condition for a fixed point there. Now let's multiply it out and solve the equations. So go across and down. I got nothing times x, 1 times y, 2 times 1. So that gives me y plus 2. The second row, minus x, nothing, 3. It's minus x plus 3. And the last line, 0, 0, 1. And that equals x, y, 1. So the first row gives me one equation. Y plus 2 is equal to x. Second row gives me another equation, minus x plus 3 equals y, and the third row is just 1 equals 1. So I need to solve these equations simultaneously. I'll do this by substitution. So from the first one, x is equal to y plus 2. So from 1, if I bracket that off, x is y plus 2, so I got minus x, which is minus y plus 2, plus 3 equals y, minus y minus 2 plus 3 equals y, so that's 1 on the left hand side, take the y over, it gives me 2y, so y is equal to a half, and then substitute into 1, sub in 1, so that y plus 2 is equal to x, so a half plus 2 is equal to x, so x is equal to 2.5. So the fixed point, I've only got one fixed point, it's a coordinate, 2.5 and a half. So that's T1 has one fixed point, just the coordinate. And T2, again same thing, take the matrix T2, operate this matrix on the coordinate xy, 1 so I can carry out the multiplication, and the same coordinate has to come out. Okay, multiplying across then, across the first row, nothing, y3, so that's y plus 3. Second row, x, nothing, minus 3. And third row, 0, 0, 1. So the first row gives me the first equation, y plus 3 equals x. The second row gives me x minus 3 equals y, and then 1 equals 1. So if I do the substitution, your x equals y plus 3 into the second one. So from 1, so your y plus 3 minus 3 equals y. So that gives me y equals y. Right, I don't get a value this time, but that is a consistent equation. So looking back at the first two equations, if you look, the first equation, I can rearrange that to be y equals x minus 3, and the second equation is also y equals x minus 3. So the set of points which satisfy those equations then is the line y equals x minus 3. So the fixed points are points on the line y equals x minus 3. So T1 had fixed points of 2.5 a half, so that was a coordinate, and T2 is a line y equals x minus 3. So the first one, because it's a coordinate, it's a fixed point, that must be the centre of the rotation, and the second one, because the line is a fixed point, then that must be a reflection. Therefore T2 is a reflection because fixed points are on a line y equals x minus 3. So y equals x minus 3 is your mirror. So part B, parabola C as that equation, and I want the image under of T2 C dash show that. Okay, so I'm taking the matrix T2, 0, 1, 3, 1, 0, minus 3, 0, 0, 1, and I got to operate this on this equation of the curve y squared equals 8x. Now you can't operate a matrix on an equation of a curve. We need the coordinates, so I do the parametric equation. So x equals t gives me y squared equals 8t, so y is the square root of 8t. So the parametric coordinate is t comma root 8t. So I operate this matrix on this coordinate. T and a 1, and then what comes out, okay, will then be my new equation. So I'm multiplying this out then, so I've got 0 root 8t3, so that's root 8t plus 1, sorry, again 0 root 8t and 3, so that's plus 3. Second row, t nothing minus 3, and the last line 0, 0, 1, and that's going to be my new coordinates. So I got x is root 8t plus 3 and y equals t minus 3. So there's the parametric equation of c dashed. So I need to get rid of t. So from the second one is easier than the first one, so rearranging the second equation, I go y plus 3 is equal to t, and then I'll substitute that into the first one. So I got x is equal to the square root of 8 times t, which is y plus 3, add 3. So take the 3 over the other side first. X take away 3 is the square root of 8 y plus 3, and then square both sides. That's x minus 3 all squared is 8 bracket y plus 3. Expand this bracket, so that's x squared minus 6x plus 9 equal to 8y plus 24. So I'll collect it all onto one side. That's x squared take away 6x take away 8y plus 9 minus 24 equals 0, and that gives me the required equation. Okay, when you're operating a matrix on something, it has to be a coordinate, not an equation. So the way around that is to write the parametric coordinates of the curve that we want to transform.